All right, guys, welcome to part 2 of the chapter 5.2 notes video. Let's get started with this practice problem. Okay, so it says phosphorus, an element used in matches, has an atomic number of 15. Write the electron configuration of a phosphorus atom. All right, so we're going to use the periodic table to do this. I'm going to write a text box here. So here's our periodic table. So the first thing we want to do is we need to find phosphorus. Okay, now it might take you some time to find it, but phosphorus is element number 15. Okay, it's right here. And we're going to write out an electron configuration for phosphorus. So when we're done, we're basically going to have an answer that looks something like this. 1s2, 2s2, 2p, blah, 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 blah. So the rows of the periodic table are the energy levels. Okay, so row 1, row 2, row 3, row 4, row 5, 6, and 7. And the sections of the periodic table are the different orbitals. So the first two sections here, column 1 and column 2, these first two columns, those are all elements that have electrons in S-shaped orbitals. So we call this the S block. All the electrons over here to the right, so from boron to neon down to radon over to thallium, this big square that's on the far right, all of these are elements that have electrons in P-shaped orbitals. So this is what we call the P block. Helium up here is technically over here right next to hydrogen. So helium is not part of the P block. It is actually part of the S block, even though it is shown on the far right. Helium technically sits right here next to hydrogen. Okay. All the elements that are here in the middle, so from scandium to zinc down to copernicium over to actinium over here. So all these ones in the middle in this rectangle, these are all elements that have electrons in D-shaped orbitals. Okay, we call this the D block. And then lastly, all these ones down here on the bottom, these are all elements that have electrons in F-shaped orbitals. So we call this the F block. So basically, to write an electron configuration, all we're going to do is we're going to find the element, and then we're going to read the periodic table like we'd read a book. Okay, so you read a book from top to bottom, left to right. So for phosphorus, our first electron is going to be in the first energy level, right? Row number 1. First element is hydrogen. So that's 1. We're in the S block, and that's the first element, the first electron. So we're going to write, and I'll zoom in again here so we can see a bit better. Maybe not that far. See if we can zoom, whatever, it's fine. Okay, let's just make our thing bigger. All right, so the first one's going to be 1s1. So 1 because we're in row 1 of the periodic table. S because we're in the S block for hydrogen, which is in the S block. And the little exponent 1 because it's the first electron out of 15. Okay, phosphorus has 15 electrons. That's why the atomic number is 15. Then the next electron is still in the first energy level, so row 1. It's in the S block because now it's where helium is. Again, helium's on the right here, but it technically is right next to hydrogen. So this says 1s and then 2. It's because it's the second one. So we have 1s2. Now, if we keep doing this is going to get really long really fast. So a lot of times, instead of just writing 1s1, 1s2, we just write 1s2. Okay, to show that the first two electrons are in the first energy level S block. Now, after this first row, there's nothing after this, right? Like there's nothing to the right. So then we have to go down to the next row, which is row number 2. So now we're in the second energy level. Okay, so now we're in 2. And we're still in the first two columns. That's the S block. So we're in 2s. Okay, we're in 2s. And we're at lithium. So this is 2s1. Okay, first element in the S block. 2s2, second element in the S block. So we're going to write 2s2. And at this point now, we're at beryllium, okay, because 2s2. Then we jump across this gap, and now we're over here. Now this is the P block. So now we're in row 2, P block. That's 2p. So we're going to write 2p. And boron is 2p1, first element in the P block. So 2p1. Carbon is 2p2. Nitrogen is 2p3. Oxygen is 2p5. Fluorine is 2p6. Oxygen is 2p4. Fluorine is 2p5. And neon is 2p6. right? And we're going to go all the way to neon because we still have to get down to phosphorus. So we're just basically going to keep on going till we get to phosphorus. So we have 1, 2, 3, 4, 5, 6. So we're going to write 2p 6. Then after neon, we go down to the third row, which is sodium. So now we're in energy level 3, third row. We're in the S block again, so we're at 3s. Okay, so 3s. And sodium is the first element, so 3s1. Then we go to magnesium, 3s2. So we're going to write 3s2. Then, again, we jump across this gap, and now we're in the P block again in row 3. And so this is 3p, and phosphorus is 1, 2, 3 elements in to the P block. So it would be 3p3. And at that point, we're done because we got to phosphorus. Okay, so this is the entire electron configuration for phosphorus. 1s2, 2s2, 2p6, 3s2, 3p3. So this basically tells us where all 15 electrons are in phosphorus. And by the way, we know that there are 15 electrons because if you count up all the exponents, you should get 15. So we have 2 plus 2 plus 6 plus 2 plus 3 equals. Okay, so 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 3 is 15 electrons, which I'm going to write as E minus. Okay, that's the shorthand symbol for electrons. All right, so this is our electron configuration for phosphorus. And we're just going to write P for phosphorus. Okay. All right, guys. So I also want to show you one other part about writing out electron configurations, and that is what we call an orbital diagram. So this is going to be where we actually show the electrons as arrows and putting them in boxes or on underscores to represent the different orbitals. Okay. So I'm going to show you what this looks like. Again, it's just another visual way of representing electron configurations. So we're going to have an underscore here for 1s, and then 2s, and then 2p, and then 3s, and then 3p. And I will label these. So we have 1s, 2s, 2p, 3s, and 3p. Okay, now again, you can draw these as boxes, but it's harder to draw boxes on Google Slides. So I'm doing them as underscores. But each of these lines represents an orbital. Okay, so there's one underscore for the 1s orbital. There's one underscore for the 2s orbital. You notice that we have 3 for the 2p orbital, and that's because remember that there are 3p orbitals. Each line represents one of those orbitals. Then there's one line for the 3s, and then again another 3 for the 3p. You notice I put big spaces in between the different sublevels, but between the orbitals inside, there's just smaller spaces. Okay. If we had d orbitals, which we don't, but if we did, let's say for example we had 3d, then it would look something like this. Can we label this 3D? So there's 5D orbitals. We'd have 5 underscores, and these would represent the orbitals, and then we're going to put arrows in here to show the electrons. Okay, so again, this is what we call an orbital diagram. So this is an orbital diagram. It's just a visual way of showing electrons. So this electron configuration we have right here for phosphorus, we're going to show as an orbital diagram. So we're going to go insert, arrow, and we're going to draw some arrows. And you know what? Let's actually zoom in here to make it a little bit easier to see. Perfect. Okay, so we have an arrow. So we're going to draw an up arrow, because this is one electron in the 1s orbital. Then we're going to draw another arrow going down. Okay, so that's the down, that's the other electron. So this is showing the first 2 electrons in the 1s orbital. Okay, and we have to follow, remember, our 3 rules. We have our Aufbau principle, or Pauli exclusion principle, and Hund's rule. So Aufbau principle says we have to start at 1s, and we got to work our way up, and we have to fill all of these up first before we can go to the next one. So what that means is that I can't go one arrow here and then go put another arrow then over here, okay? Because this orbital has to be filled before I can move on to the next one, and in order for it to be filled, I need to have 2 arrows in here, not just 1. So that is the Aufbau principle. Okay, you have to basically go in order. Pauli exclusion principle says you can only have 2 electrons at most. So once I've got my 2 arrows here, I'm not going to go and add a third one and have it be like this. Okay, I'm not going to do that. I can't have more than 2. And Pauli exclusion principle also says they have to be spinning opposite directions. So you'll notice one is spinning up, one is spinning down. They're opposite directions, okay? All right, so then let's move on to the next one. So we have 2s, and there are 2 electrons in this one. So there's 1. Insert another arrow. And there is 2. Okay, so there's our 2 there. Then we get to 2p. Now this is where Hund's rule comes into play. So Hund's rule says that you have to put individual electrons first in each of these boxes, and they all have to be spinning in the same direction. Okay, so we're going to go up, up, up in each of these. We could go down, down, down. Okay, there's no rule that says like they have to be pointing upwards. It's just kind of personal preference. So, but Hund's rule says you have to go up, up, up. Then we can go back and pair them up with a second electron that is pointing in the opposite direction. So down, down, and down. Okay, like this. Okay, that is what Hund's rule says. So just to make sure again that makes sense, if we undo this real quick, that means that we can't do this. Okay, we can't just go, okay, 1, 2, and then insert arrow, 3, 4. So we go 1 up like this, and then we do another one that goes down. Okay, we can't do that. It's got to be individual singles first. Then we go back and pair them up. So it's just, again, it's good practice to get into. And there are ones later on that you'll do where you might not have enough electrons to fill this fully. So it's important to make sure that we do this in the right order, because if you run out of electrons, and let's say, for example, like we stopped here, right? Let's say we stopped here. Then these 2 would be correct because of how we've done it. Whereas if we start pairing them up right away, we might like go 1, 2, 3, 4, run out, and then we leave it that way, and it would be wrong because we need to have these 2 in individual orbitals, which I think will pop up actually at the end of this. So anyway, all right, so let's continue here putting these arrows in. Okay, so there's the 2p6. Then we have 2 in the 3s orbital, so 3s2. So there's 1. Here's 2. And then lastly, in our 3p orbital, and again, here's where Hund's rule comes into play, we have 3 electrons. So we're going to go 1. We're going to go 2. And lastly, we are going to go 3. Okay, so there is 3p3. So those 3 electrons are individual. They're in their own orbitals, and they're all pointing in the same direction. Okay, so again, this is what we call an orbital diagram. There are problems that may pop up where you have to do this. So, all right, let's move on to the next one. Okay, so moving on then, it says exceptional electron configurations. So there are some exceptions to some of these rules. Okay, so basically what this is saying is there are some elements that have electron configurations that are different from what they should be, meaning that they're either breaking the Aufbau principle or they're breaking the Pauli exclusion principle or something or other. And there's a reason why they do this, okay? And so basically, some elements will have electron configurations that are not normal because of this general principle. So half-filled sublevels are not as stable as fully filled sublevels, but they're more stable than partially filled ones. Now you might be thinking to yourself, what the heck does that mean? Let me explain. Okay, so I'm going to shift this up here so we can actually do some typing. So let's think of the s orbitals. Okay, s orbitals. There's only one s orbital. Okay, so s, there's one orbital. And remember, the Pauli exclusion principle says at most 2 electrons can fill an orbital. So the most number of electrons that can fill any s orbital, whether it be 1s or 2s or 3s, is 2 electrons. Okay, so 2 electrons would be fully filled. That'd be fully filled. You have 2 electrons. If you had only 1 electron, that would be half filled, right? Because again, at most, it can have 2 electrons. So 1 electron is only half of that. So that is half filled. Okay? Hopefully you're following along. That makes sense so far. Okay. So that also means then that other, let's make this smaller too. I'm also going to zoom in. Sorry, I apologize. I'm just going to make sure that we can see all this. Okay. That also means though that other orbitals will also do this. So let's think of p. Okay, so p orbitals, there are 3 p orbitals. Okay, so 3 orbitals. Remember that each one can hold 2 electrons. So total, there are 6 electrons that can be held in the p orbitals because there's 3 of them and each one holds 2. So if there are 6 electrons in the p orbitals, that is fully filled. Okay. If there were only 3 electrons, that would be half filled. Okay. And fully filled orbitals are the most stable. Half filled are second most stable. And anything that isn't half or full just isn't special. Okay? So we'll do the same thing with the d orbitals. So d orbitals, there are 5 d orbitals. There are 5 d orbitals. Each one holds 2 electrons. That is a total of 10 electrons that can be held in the d orbitals. So that would be fully filled. Half of that would be 5 electrons. That is half filled. Okay? And anything that isn't 10 or 5 isn't special. So for p orbitals, anything that isn't 6 or 3 isn't special. So what this is basically saying is some elements will fill these electrons up to be either fully filled or half filled, or they'll move electrons around so that some of these are fully filled or half filled, and they kind of break the rules. Okay? One of these ones is copper. So we're going to take a look here at copper to get an idea of what this actually looks like. Okay, so copper is an exception to the Aufbau principle, and it has an electron configuration that is not what you typically would think it is. So I will write out the electron configuration for copper based on what it should be, and then I'll show you what it actually is. So I'm going to just go duplicate slide here, and we're just going to get rid of this image. And we're going to type in this text box, okay? So let's do this. So let's go expected copper configuration. And then we'll go actual copper configuration. All right, so we're going to write in what we expect copper's configuration to be and then what it actually is. All right, so let's look back at the periodic table. Let's find copper. Copper is here. It's element 29. Okay, so I'm going to do this one kind of quicker. But for copper, we would have 1s2. Okay, so again, we always start up at hydrogen. So row 1, s block. 1s1, 1s2. Remember, helium sits right here. So 1s2. So 1s2. Then we go second row. So 2s2. 2s2. Then we go to the p block, so 2p, 1, 2, 3, 4, 5, 6, so 2p6. Then we go row 3, 3s2, right? Go to magnesium, that's 3s2, so 3s2. Then we go to the p block, so 3p, 1, 2, 3, 4, 5, 6, so 3p6. Then we go to the fourth row, so now we're at 4s2, we're at calcium, okay, 4s2. And then we get to the D block. All right, now, the thing with the D block, okay, and this is, again, just where things get confusing, and you just have to remember. The number for the D block is always 1 less than the actual row number. So we're in row 4 right now. We might think that this is 4D. It's not. It's 3D, okay? So this is actually 3D. 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, and copper is 3D9. So 3D9, okay? This is what we would expect for the configuration for copper. However, this is not actually what it is. What it really is, and I will do it down here. So it's all of this. I'm just I'm going to copy paste this because it's the same thing for the most part, except for one tiny change. This is the tiny change that happens. Copper will take 1 electron from its s orbital in the 4s, and it will move it up into its d orbitals. And here's why. Up here, we have 4s2, which this is full. Okay, that's fully filled. Because remember, S-shaped orbitals can at most hold 2 electrons. So 2 electrons, fully filled, most stable. But the d orbital here has only 9 electrons, which 9 is not fully filled, because fully filled would be 10. Okay, fully filled is 10. And half filled is 5. So at 9, it's not full and it's not half, which means it's nothing special. But if copper takes 1 electron from the s orbital and pulls it up into the d orbital, now we're left with 4s1, and 1 electron in your s orbital is half filled, which is still pretty stable. And we now have 10 electrons in our d orbital, and 10 electrons is fully filled, and that's the most stable. So in this first one, we have a full filled s orbital and a partially filled d orbital, which is nothing special. And down here we have a full filled d orbital and a half filled s orbital. And fully filled and half filled are better than fully filled and partially filled. Okay, so this is the reason why copper decides to do this configuration rather than this configuration. And in fact, every single element in this column, so copper, silver, gold, whatever this one is, rhodium, they will all do the exact same thing. Okay. Also elements in this fourth column for chromium, molybdenum, tungsten, seaborgium, they'll also do the same thing. They'll pull one of their s orbitals, one of their electrons in their s orbital, they'll pull it up into their d orbital. So they have 5 in the d orbitals and only 1 in the s orbital, because those are both half filled, and that's more stable than a fully filled s orbital and only a partially filled d orbital. Okay, so again, I know this is confusing. I can explain more in class, but this is something that you do need to be aware of, because you might see an electron configuration for one of these elements and go, wait, why is it that? That's why. Okay. Okay, so that is it for this section of notes. I know that was kind of a long one. There's a lot of info. Hopefully that helped, though. In the next video, you will see me going over the practice problem. So, all right, guys, thanks for sticking with me. As always, if you have any questions, feel free to email me, talk to me in class, reach out, make sure that you get those questions answered. All right, I'll see you in the next